Oh, yeah. Okay. I've got a title. Yeah, that's right. Yeah.
Good afternoon. It's my pleasure this afternoon to introduce one of our departmental faculty, Dr. Ling Yuan. Ling came to us 15 years ago, and he came as really part of an effort to develop KTRPC into, I would say, a biotechnology, plant developing to look beyond tobacco, but use tobacco as a monoplant to really stimulate economic opportunity in Kentucky. He's been very active in that role. He's also been very active in ABT as a teacher, and just recently became director of the KTRPC overall. So it's my pleasure to introduce Ling this afternoon, and look forward to the seminar.
Thanks, Mike, for the introduction. One more person, two. Okay, so just as the title implied, that actually my talk's going to be very straightforward. One is hamburger, good. Raised cattle, not good, right? So actually, it's not as simple. So let me start. So we all, actually, some of the numbers that put out is relatively updated, but I'm not sure it's exactly accurate. But nonetheless, right now there are about 10 times more farm-raised animals on the earth, I mean, on this globe, than human. So for the approximately 7.4 billion people, we have 65 billion farm-raised animals. And so with this animal, certainly it brings a lot of impact to our environment. And so you can see that some of the major impacts would be of the farm animals would be to the environment and the climate, mostly negative impact. And they also impact to global nutrition. So in this regard, it comes with both positive and negative impact, and which is easy to understand. And animal welfare largely is negative impact because with such a high density of farm animal production, it's difficult to have a very good animal welfare. And for human health, then that combines with both positive and negative impacts. And you can see that, in fact, we're living healthier and longer, stronger, to a large extent is due to consumption of animal meat and proteins. But on the other hand, overeating is becoming a problem. So the key point I'm trying to make here is, so when you compare to just vegetarian diet, straight from plant to our body, we went through a extended food chain, which is we turn nutrition from plant into animals and then feed us. And this so-called lengthened food chain usually require a lot more natural resources, and that's easier to understand. And obviously, farming, especially animal farming, contributes significantly to greenhouse gas emission. And in fact, if you look at what EPA put out, this is agriculture and and also forestry and other land uses relate to farming and agriculture, and it's actually really significant. So almost as much as electricity and heat production, and it's significantly higher than what is contributed by transportation, like airplane, cars, and trucks and trains. And this within that, actually, a big portion of this 24% contribution of greenhouse emission is due to animal farming. By the way, I'm glad that in the audience I have good friends from animal science and ag bioengineering and also ed econ, just to scrutinize some of the things I'm going to say, and also I really value their feedback. The only thing, some people may throw tomato at the end towards me, and this is my nice shirt, so be easy. And but anyway, so the next thing is you look at in the last 50 years, starting from the 1960s, and you see the meat production, and you can see the meat production in metric tons increased about 5 times. And the most significant races from Asia, which is, you can see that actually China, Japan, countries that move into the more advanced status accompany that is meat production. And so you can see that in the last 50 years, and in Asia, the rate increase of meat production is about tenfold. So there are a lot of meat being produced, and that put into stress into some of our natural resources, and most significantly our waters and land. And you can see that on a per kilo base, it takes a lot more water to produce beef than say soybean. About 7 times more water has to be used to produce a kilo of beef. And at the same time, a large area of our farmland, including cropland and pastures, being used for either animal growth or feed production. So all this definitely, and I'm not going to read this, but nonetheless, you can see the impact of farm animal production is severely impact our natural resources. So with that, somebody can open the door to cannot get it. So, with all those problems and we clearly want to see, there would be nice to have some kind of alternative, for example, plant-based alternative to replace what we having now, which is animal meat-based. But we clearly know that we can't kid ourselves. I mean, you tell everybody to become a vegetarian today, and nobody will listen to you. And after all, we are meat eaters, and so there are a lot of reasons that we're meat eaters, and in the beginning I implied that actually it contributes to a large extent our better development of mankind with stronger bodies and better health in some way. And also there's some other issue that limited our turn to the alternatives like plant-based meat production. And so there are a lot of problems that is associated with that. First of all, we all know the vegetarian meat, they don't, the ones currently available, they don't taste like meat. They just simply don't taste like meat. So it's really difficult to convince people to convert to that. And second thing is we fail also in develop meat substitute that fulfill this kind of requirement to be a successful product. For example, meat taste and aroma. So when we eat in the mouth, do we taste the meat? Do we smell the meat? when you have a plant-based burger. And texture, so when you chew on it and you feel that you're chewing on meat, and that's the mouth feel is very important. And price is always important. I mean, after all, it's the taste and price that determine the next generation products and the successful market of the kind of product. And we have big enough economy of scale that we have big enough supply for a global supply of this new product. And social acceptance, of course, is easy to understand. So when you look at meat, really what makes meat taste like meat? And there are a lot of factors, but one of the key factors is myoglobin. Myoglobin is a heme-bound protein that bonds iron and oxygen, and it's present in the muscle. And it's structurally, it's very similar to hemoglobin, which is in our blood, and carry oxygen. We all know that. We hear a lot more about that. But in fact, in our bloodstream, we don't really have myoglobin. Instead, we're all hemoglobin. And in fact, the only time that you see myoglobin in your bloodstream usually is because severe injury. So you have a big cut that your myoglobin will contaminate your bloodstream. And normally you don't find that. But structurally, they're very similar. They're very alpha-helical proteins that can bind iron, and the iron actually linked to oxygen. And so when you look at a rare steak, when you go to a restaurant, you cut it, and usually we call it the bloody steak. And what you see, the so-called blood, actually is not blood. Those are myoglobin, sorry. And so in fact, in a steak, it doesn't really have much blood there at all. Instead, we're seeing the myoglobin release to your plate. And so that's what gives you that bloody feel and the meaty flavor. And so that is something to do with myoglobin. Now, in red meat, like beef that we eat like a steak, it has about 0.5% of myoglobin in the muscle. Chicken, on the other hand, is about 1/10 of that. And that's why we call them white meat. They don't really show this, strong pigmentation. And also because of that, when you grow a meat compared to a steak and a chicken, and you can clearly feel that when the heme is released, it catalyzes a series of reaction that give you this meaty flavor. Now, so that's what makes a hamburger taste like hamburger, or a steak taste like steak. And that's where you see a little bit of the redness, in the hamburger patty. And so that's why our plant-based protein substitutes just don't have this kind of taste and feel. However, plant actually has similar type of protein. And Hong Yan's here, and he's an expert on this particular protein. And the legumes in their roots, they have the LV protein that help the root to concentrate oxygen and use in nitrogen fixation. And these proteins are, if you look at the nodules, and Hong Yan showed pictures before, and when you look at the legume root nodules, and you will often see this kind of redness, and you can see it here. And you can extract them out, like a enriched heme protein solution that, not only look like blood. If you keep a little bit in your tongue, it tastes exactly like blood. And so actually, plant has similar protein. And in fact, the hemoglobin is very much like myoglobin. Usually exists in a monomeric form, so it's a single protein. And hemoglobin tend to form a tetramer, 4 proteins linked together. But myoglobin is, and also, in fact, the hemoglobin has higher efficiency bind oxygen than the animal protein. So we have this protein in plant itself, and by itself, it tastes like blood. And in fact, if you make a vegetarian burger and add this protein, add the LB protein in it tastes like red meat. And that's where I'm going to introduce you to the next slide, which is a video by Time magazine. And also this is a product that is introduced by this company called Impossible Food. And I'm going to show two clips and give you some sense of what can LB protein be used in a meat substitute. Whoops. Back one. Oh, wait.
I think if you just click on the actual.
And the next one tells you how this product is made. This is an outdated statement. This is an old clip. And in fact, 2 months ago, FDA approved the ingredient. So now you get a sense, what this Impossible Food burger is. And so now you're going to ask, why that had to do with me, plant scientist. And so in fact, we came up with Impossible Food and obtained a grant from them for 2 postdocs for about 3 years. And we worked on this. The whole idea is to reprogram the soybean seeds to be the factory to make this protein. And currently available products, fermentation products, that use yeast. But for large scale production and to feed the whole world, we need to have a better solution to that. And the whole so-called reprogram process actually is pretty simple. We basically take a protein that's normally produced in soybean roots and then make them produce now in the seed. And then of course the seed is where supply the protein and eventually going to make into the meat substitutes. And in fact, right now, most of the vegetarian official meat is from soy protein. And so soybean is a natural, really good platform for this kind of protein production. And so the whole concept is very straightforward, very simple. So the way we do it is we first clone the soybean LB gene, and in fact there are several isoforms. But we clone those genes, and then we express that in soybean seeds using a seed-specific promoter. Listed here as a glycine promoter to drive the expression. And so we produce it in 2 forms. One is we allow the protein to accumulate in the cytosol of the plant cell. So just let it accumulate there. The other one we did it is to guide the protein into this so-called protein storage vacuum. The vacuum itself is kind of like a garbage bag in the plant cell. It collects all the junk and some protein that the plant cell doesn't need at that moment, and they store in this vacuum. And you can actually put a small stretch of amino acid in front of the protein, we call signal peptide, that will guide the protein to here to the membrane, and the protein will pass through the membrane, and eventually the signal peptide will clip off, and then the protein is stored in there. And that's how we did it with 2 types of expression. But of course, this process took a long time, but nonetheless, we were able to generate soybean seeds that accumulate LB proteins. And these are the 2 constructs that we use. And this the yellow here is for the LB gene, and the difference between the upper one, which is cytosolic protein, versus the vascular protein is this signal peptide in front of it. And when you have a big signal peptide, will guide the protein into the vacuum. And so they both are driven by a seed-specific promoter, so it will only express in the seed. And so here, the two constructs allow us to generate some very striking phenotypes that you can compare to the wild type and the empty vector control, which is just like a normal soybean. And we see a little bit of red phenotype in the cytosolic beans, and much stronger color can be seen in the vascular beans, the accumulation of LB in the protein storage vacuum. And the protein can be extracted out of the soybean seed directly. You can see it's a red protein. And so when you put it into a spectrophotometer and scan for the spectrum, which the heme itself is a very distinct 415 nanometer peak. And the green line here shows a control, which is the purified recombinant protein. Also give you a 415 sharp peak here. And then this black line is the control without the LB protein. You don't see that. And then the red line is where a crude protein that just extract from soybean. And you can see this bump in here in 415 indicating that the red color from LB is indeed mixed into the total protein. And also you can compare them by looking at the gels and how much protein is produced. And you can see there's a cytosolic line that, although accumulate protein is much less than the vascular line, which produces a lot more protein. And you can see that this is the recombinant protein control, which runs a little bit bigger because it has a 6 histidine tag there for purification. So it always runs a little bit slower on the gel. And then we also investigate, so because we use a seed-specific promoter to drive the expression, so we see is that seed-specific. And we look at the flowers, seeds, and leaves, stem, roots, and the only place we can detect is in the seed. So you ask, why not the roots? Because it's a root protein, right? But those plants that we use are greenhouse-grown plants. They don't actually nodulate. So there's no nodule formation of those greenhouse plants, so they don't accumulate LB protein in the roots. So again, we demonstrated this indeed is a seed-specific expression. And we artificially separate the developmental stage of the seeds to S1 through 5 stages. And the very young and immature seeds being S1, the dry seeds being S5. And you can see the protein accumulation. So at S1 stage, it doesn't have any. And then start S2, start seeing some formation. And then 3 through 5, you can see the highest accumulation of the protein. And this is the empty vector control. And we also look at the gene expression of the LB genes in the seeds. And you can see that in S1 stage, it doesn't have much expression at all. And then start to build up the S3 and 4 stage, where when they get the dry seeds, it doesn't have much expression. But nonetheless, the protein is still being stably trapped in the seed. The next, let me see. Okay. The next question we ask is this protein indeed authentic, just like what we found in the soybean roots? And so we purify the protein from the transgenic seeds and use mass spec to determine the molecular mass of the protein. And the principle is relatively straightforward. We use the so-called bottom-up approaches. Basically, you take the whole protein and you digest them with proteinase. They will cut specific sites and you cut it into fragments. And then further, each fragment will be run on a HPLC and they separate it and then further fragment that, and then we can determine the mass of each piece. And this panel kind of shows you what the overlapping pieces we can detect in the whole protein. This is the protein sequence. And you can see stretches of peptides we can detect in there. So they're overlapping. So when you put them together, and then we give you precise the sequence and also the molecular mass. In fact, we have a very monomeric type of molecular species that with a molecular mass of 15,232 or something like that. Can't really read it, but it's exactly what the predicted molecular weight is supposed to be. And in the whole protein, we can also detect the heme moiety there. And the next thing we did was to compare how well this protein found heme in the protein, and how we call it heme loading. So how efficient it is. So we run the purified proteins, the LB proteins from the transgenic seeds, from the root nodules, from the root, and also the recombinant proteins. And this is the one that is produced. In fact, that's what is being served in the Impossible Burger right now. And we monitored in two spectral wavelengths, and one is looking at 280 that detects the protein. The other we monitored at 415, which detects the red pigment. So you can see that each of them, we can compare the ratio of the area that we know how efficient they load heme. And the native nodule LB has about 2.2, and the transgenic soybean LB versus the yeast produced LB has a very similar value. It's about 3.5 or so, which is actually higher. So, but we're not going to take this number literally, because we believe that during the purification from the nodule, we probably strip off some of the hemes. But nonetheless, this data indicating that the efficiency of heme loading is very, very high, and the transgenic plant produced protein is really no different from what is being served right now in the Impossible food. We also asked the question, because heme biosynthesis and chlorophyll biosynthesis actually is highly linked, and in fact started with the amino acid glutamate and be activated using a tRNA. And so this is a 9-step conversion that get to this point, it's going to branch out. One enzyme going to determine, this substrate will go to the heme production. The other several enzymes come to lead the pathway towards chlorophyll biosynthesis. So the reason we ask this question is because we want to know, first of all, is the soybean seed plastic enough to handle large amount of heme-loaded protein? Because that's not normal in a soybean seed. So do they have enough heme to handle that? That's one thing. Second thing is, will that affect chlorophyll biosynthesis, which may or may not affect development? So those are the questions that led us to ask this particular question, that whether or not the gene expression during LB accumulation have differed compared to what we're seeing in the controls. And so first thing you can see that here, we monitor several upstream genes in here. So each bar here is a different stage from S1, 2, 3, 4, to S5 for each enzyme. And you can see that the expression was quickly induced in S1 and 2 to a very high level for the upstream enzymes. And so is for the catalase that actually biosynthesize heme. So they all responded very quickly in the S1 and 2 stage. And then towards the end, actually dropped down to the control level, which is 1 here, so a line here. So that tells you that the seed apparently sense there's some heme proteins being produced, and immediately turn on the upstream pathway to supply enough heme, all the way to here, to supply the heme for the protein production. But as soon as the production is done, it accumulates enough, it feels it doesn't need so much heme anymore, it shuts down. So it doesn't overproduce heme. But on the other hand, when we look at the two key enzymes, the methylene catalase and the chlorophyll synthase, that makes chlorophyll. And during all 5 stages, it didn't change. Okay, it remained more or less the same when you're looking at gene expression. So it tells you that this pathway is relatively plastic, and it allows the pathway to go from, as soon as it sends the LP signal and quickly guide pathway towards the heme production. So seeds are capable of handling this type of high accumulation of the foreign protein. So now go to a little bit of economic. So would this bean, this red bean, would that be good enough? Even though it's a first generation, would it be good enough for a large scale production? So let's do some comparison. That's where the econ colleagues are going to kill me. But anyway, when you look at the current yield of soybean, it approximately produce a little bit less than 3,000 pounds per acre. Okay, and soybean usually takes about will produce about 40% protein, plus or minus. And so we use that to calculate that. That will give us about 1,000 pounds per acre of total protein. There's total protein. So we have evidence to show that the highest beans that we are able to produce so far accumulate close to or a little bit sometimes over 1% of the total soluble protein. So with that, we will get 10 pounds of this LP protein per acre. Okay, and so I mentioned that beef, the red meat, has about 0.5% of myoglobin. So if you use that to calculate 10 pounds of LP protein, will be able to supply for approximately 7,700 quarter pounders. Okay, so per acre, it's enough for about 7,000 quarter pounders by McDonald's. So you look at what McDonald's is selling now, 6.5 million per day, quarter pounders. And that would take about 900 acres to supply, to take over all the quarter pounders per day, and then over 300,000 acres to a year to supply all the quarter pounders. And but this number actually is, is surprisingly small because, as of 2018, U.S. alone produced about 90 million acres of soy. So we have plenty of lands and capability of to make LP proteins in just in the U.S. to support close to 300 McDonald's whole company. So it seems to me, people can certainly debate on this number, but nonetheless, in the ballpark range, our economy can handle this type of production. So who cares about this? Actually, a lot of people. And so Google actually, as soon as Impossible Food was, making the headline news, Google came in, tried to buy them, and they refused. So now Google invests into it. Khosla Venture, of course, known for investing a lot of money into clean technology. They're in it. YK, the Crazy Rich Asians, and Bill Gates. Bill Gates certainly invests into it, and some other banks. And so right now, there are a lot of investors buying into that. So more significantly, actually, this is no longer just something that people talk about. White Castle sells that now this year, and you can go there and you get the burger. There's certainly a lot of debate whether or not it's a good choice, or definitely a lot of controversy. But nonetheless, this is coming. This is here, and it's a real product. Now, whether or not the economy is there and how well we sell remains to be seen. But using currently all the LP proteins are made with the fermentation, and that is very difficult to supply. All the McDonald's, for example, and eventually they will need to have a plant-based solution to it. And I think we at least paved the way to achieve that goal. So at the end, I give you a little clip just to see how people react to the burger. This is a little bit older clip, but let's. So that's it. I just want to acknowledge that the work mainly carried out by a former postdoc, Jay Gosh, and with help of Maroon and Pinto in my lab. And so with that, I want to start some discussion. George?
Why does the soybean seed have some a robust capacity to make chlorophyll, or like?
Oh, when it's immature, it produces plenty of chlorophyll, and it's green seed, and so it has the capacity to make green chlorophyll. That's
why is it green? Does it contribute that much of its own glutamate to?
Oh, that's a good question. Hey, Tomo, why is this green?
Well, so
Sure.
what I know from Arabidopsis, not Soybean, if you mutate some of the plasmid genes, it's lethal. So we know that some of the things generated in the plasmid is important for seed development, but we don't know exactly what components from the plasmid, which is equivalent to chloroplast, are important. So definitely see science.
Sure. Anything
Yeah,
to add?
nothing else to add.
Okay. Mike?
Can they make the cheese without animals? And is it really healthier?
Oh, yeah, for Kristen, Mike asked, can you make cheese out of it? You mean compare the cheese?
Well, they're making cheeseburgers, so I don't know where that, is that
Oh,
cheese
okay.
or is
Okay.
that?
So the cheeseburger, he said the cheeseburger, that's the cheese is no animal, so this is not a total veg burger, right?
Right.
Sure, so we'll find some vegetarian cheese.
So, but is it healthier? I mean, they put the coconut in there, which is.
Well, so Mike said that it's healthier just because, for example, coconut oil is in as a substitute and also give you the texture. Well, whether or not it's healthy is really up for debate. I mean, there are a lot of things definitely you can debate whether or not red meat is really truly that unhealthy. That's totally up to debate. But coconut oil itself, that puts into a so-called tropical oil that in this country has a very strong negative sound and image. And that actually is unscientific. And there's, I mean, it is because I worked in this industry before, there's a little bit of push from our own oil industry to label the tropical oil being unhealthy. Actually, it's not as unhealthy as what we claim. In fact, the whole world eats quite a bit of tropical oil, and people live just as well.
How stable is the product in the dried beans? How long do you have to extract that before it starts to degrade?
The question was, how stable is the dried beans and how stable is the protein? We haven't tested that yet. The beans, we have some in there, it looks like colored chips, but I don't know if they're really protein stable or something that we don't know. So.
Ling, it seems like the consumers of this, if these are people, primarily their target seems to be people that are interested in the environment and everything else. Those tend to be the same people that are against biotechnology and engineered food. So what's happening there? Because it seems a little strange.
That's a very good question. So the question was, the same people that like vegetarian burger are also the same people against biotech, and how do you reconcile this emotional conflict? And now I don't have answer to that, but bottom line is this product is not really designed just to fulfill the need for the vegetarians to have a burger that's similar to a real burger, but instead if up to the company, their goal, which you hate, is to completely replace cattle production.
We're ready for the competition.
No, it is. That's why we're using tomato. And
it's not going to be a tomato.
Something that's polluting the environment.
So, do you have any estimates of the cost of production in soybean versus yeast fermentation?
Actually, the company has a little bit of. The question was, is their calculation for the soybean production versus the fermentation production? A company certainly has done that, and the fact that they came out and support us to carry out this project clearly indicated they see there's no future in the fermentation-based approach because it's just too expensive. It's almost like making drug. And not to mention using yeast, you have to highly purify the protein. And what's the thing about soybean-based production, because soy protein is already used in food and for artificial meat production, you don't need to purify it. In fact, all you need is enrich. And with some, carry on soybean protein there, so what, right? You don't need to purify to a point that, they did to really meet the requirements. So you don't carry, for example, yeast protein through there to cause health questions. So in that, two ways to answer this is it's clearly a soybean-based production will be justified. You first.
So obviously, leg hemoglobin is associated with root nodules, which is associated with soil where iron is often abundant. Do you think iron uptake could be a limiting factor in production of leg hemoglobin in seeds where it stands to reason that iron would be less abundant?
Right. So the question is whether or not we know the iron supply is sufficient for the seed because the hemoglobin usually is formed in nodules in the root and has plenty of iron. We don't have we don't have a clear answer to that, but so far from what we can tell, the heme production is so efficient and so inducible by itself tells us that most likely it could be fine, and it just needs to uptake more. And but that needs to be investigated. Yeah, Tim.
You mentioned that there wasn't a signal for the leg hemoglobin in the roots because they didn't have nodules because they're grown in the greenhouse. Have you grown soybean plants that have nodules that also produce it to see if there's...
So the question is whether or not we test the soybean that is grown that also forms nodules. We haven't tested that yet. Didn't see the need, but as soon as we go outside, which we haven't done so, that will be a case. George?
So it's worth noting regarding the cheese that rennet is our oldest GM protein. It's been used to make cheese for decades.
Sure.
And so it's very much like your leg hemoglobin thing. You're producing a product from a GM plant.
Yeah.
And in itself, it's used in a basically a processing mode.
Yeah. So George commented that actually the making cheese, for example, chylotrypsin was one of the earliest recombinant protein that being produced in the biotech sector, and that is mainly for cheese production. Yes, and that makes sense.
And if you look at the list of proteins that are used in processing food or making processed foods, about 50% of them are recombinant, produced in either animal cultures or in yeast.
Yeah. So George also said that about 50% of the food processed enzymes are recombinant based. Any other questions? Dave?
Actually, I'd like to add a comment to what George said. So in Europe, that's as much as the US, and they don't label the foods as your product. So I have a question, follow-up question. So what cultivars have you put it in, and do you have a plan for commercialization of this?
Dave asked two questions. One is what cultivar soybean jack is the cultivar, and we have planned for commercialization. Not yet. First of all, I mean, this is a academic industrial collaboration, and impossible